Okay, so we're going to do a couple more optimization problems. The process is roughly the same. It's just building the function. The difficulty there can vary a little bit, right? But once you have your function built that you want to optimize, the calculus is the same. You take the derivative, you find the critical values, you test on either side of the critical values, you choose the critical values that's either the maximum or minimum, whichever one you want to be dealing with, and then you answer the question. All right, so this one's a little more complicated. A man launches his boat from point A on the bank of a river. It goes from here, and he wants to reach point B 8 kilometers downriver, so here, as quickly as possible. He could row his boat directly across the river to point C, and then run to B, so he's going straight across, and then he's just going to run along the bank down. Now, distance-wise, that's the least efficient, right? You're covering the most distance there. He could row directly there. That's the most efficient distance-wise, so he could just row here. Or he could row to some point D and then run the rest of the way. And so here's what kind of throws a wrench in it. He can row 6 kilometers per hour and he can run 8 kilometers per hour. So he can run faster than he can row. Where should he land to reach B as soon as possible? Where should he land to reach B as soon as possible?
Is there like a current going on?
No. So we're gonna assume that's what's in parentheses at the end. Assume that the speed of the water is negligible compared to the speed at which he rows. Meaning, just assume the current has no impact on him.
Okay.
Good question. All right. What are we trying to optimize here? What are we trying to optimize? Time. That's exactly right. We want to get him there in the shortest possible time, right? So we're optimizing time, which means what we need to build is a function for time. All right, we kind of already have a diagram for ourselves. And the one thing that you do need to know is a basic physics equation, because we're dealing with distances, we're dealing with rates, and we're dealing with times. And do you know how those three things relate to one another in physics? There we go, Naomi. D equals RT. Distance equals rate times time. All right. And with that, again, what we're trying to come up with is a function for time. So we can just go ahead and solve for time. And this means that time equals distance divided by rate, right? All right, let's get some labels going on our diagram. And what we're going to be labeling is the distances. Let's call the distance between C and D, we'll just call that X. And then let's come up with another expression to represent the distance between B and D, but I also want that in terms of X. So if C to D is X, and we know that the entire thing, C to B, is 8, what's the distance from D to B in terms of X? Vincent? Yeah, it would just be the whole thing, 8, take away the X. Are we all good with that? All right. And then we also know, so we know that this is 3. And we know that c to d is x. Can we come up with a value for the hypothetical distance that we would have to row across the river if we decide not to do one of the two extreme values, right? So can we come up with an expression for that? And how would we do so? Vincent, you got it?
Yeah, the square root of x squared plus 9.
Yeah, so square root of x squared plus 9. And all Vincent is doing, right, is using Pythag with this right triangle here. Right? So we have a right triangle there. We know the two legs. So we know that this third side, let's say I call it side C. We know that 3 squared plus x squared equals c squared. And I could isolate c. And I could have an expression for c as root x squared plus 9. All right. So I think we're ready to come up with our time function. And here's how we're going to do it. I'm going to call it capital T of x. And the total time, what we're going to do is going to consist of 2 trips, right? Basically, there's his rowing trip and his running trip. So it's going to be like time 1 plus time 2. Oops, plus. So the time it takes him to row, and then he gets to shore, and that's the time it takes him to run. Now, if he does just A to B, then time 2 is going to be 0, and that's fine. Right? So if he decides, if this is the optimal path, then when we optimize, it'll just turn out that that time 2 is 0, and he just rows the whole way. And we'll be able to figure that out. Okay? All right, and so both of these, T1 and T2, are going to consist of the distance divided by the rate. So T1 is the distance he rows divided by the rate that he rows. And T2 is the distance he runs divided by the rate that he runs. All right, so let's do that. So T of x equals the distance he rows. So given our current situation, the expression we came up with for the distance that he rows is root x squared plus 9, right? That's just the distance on the hypotenuse of that triangle. So the distance he rows is just root x squared plus 9. Divided by the rate that he rows. How fast can he row? 6 kilometers per hour, so divided by 6. I'm going to label these just as we go. So this is distance rowed divided by rate rowed. Plus the T2, that's going to be distance he runs divided by rate that he runs. So once he gets to whatever point D is, he's going to get off and he's going to run that distance. What expression do we have for that distance?
8 minus x.
You got it, 8 minus x. So this is the expression that represents distance run divided by how fast can he run?
8 kilometers per hour.
You got it. So that's the rate that he runs. All right, this is actually a closed interval, so let's talk about the domain. What's the smallest x is allowed to possibly be? Think about what x is, right? X is the distance from point C to the point he lands his boat on the other side. What's the smallest that could possibly be? And makes sense. Yes, 0. I guess it could technically be negative, and he could land his boat on this side and then run down, but that's definitely not going to be the most efficient way, right? What's the biggest x could be? 8, and that just means he rows the whole way, right? So the domain of my function is just 0 to 8. All right. So we are ready to do a little bit of calculus. Before we do, let me clean up my function so that it's written in a way that it's easier to do calculus with. So I'm going to say t of x equals, instead of divided by 6, I'm going to write 1/6. And instead of a square root, I'm going to write x squared plus 9 to the 1/2. And then again, I'm just going to divide the 8 into that. I'm going to divide the 8 into both terms, so that's going to give me plus 1 minus 1/8 x. So I haven't done any calculus, I just simplified the function as it is, so that now it'll be an easier function to do calculus with. Everybody with me? Online, you good? All right, let's do calculus. So we're going to take the derivative. Now, so far in these optimization problems, the derivative has not been too complicated, but here, guess what? We got to use one of our rules. What rule do I have to use to take the derivative of that first term?
Well, you can use the constant property to keep 1/6 in the outside.
Yeah, the 1/6 will just stay. It's a constant multiple, but once I get to this guy, chain rule, right? Good. So I'll bring the 1/2 down. Derivative of the outside gives me 1/12. Leave the x squared plus 9 alone. And then what am I going to multiply by? 2x, right? Derivative of the inside would just be 2x. Oh, and I forgot. This should be negative 1/2 power here. I left that off. My fault. So it should be 1/12 x squared plus 9 to the negative 1/2 times 2x. Derivative of 1 is just 0. That's a constant. It's gone. Derivative of negative 1/8 x is negative 1/8. Good. All right. Again, I'm going to clean this one up a little bit before I move forward. Namely, I'm going to take this term, I'm going to move it to the denominator since it has a negative exponent, and then I'm going to change that exponent back to a square root. So that's going to leave me with 2x over 12 root x squared plus 9 minus 1/8, right? And then I can divide out the 2, and the 12 will become a 6. All right, so let's go up here. T prime in its final form is x over 6 root x squared plus 9 minus an 8.
Mr. Toller,
Go ahead.
why can't we just say that rad x squared plus 9 is just x plus 3?
Oh, because you can't take, because remember a square root is actually an exponent, and that doesn't follow order of operations. So if I have x squared plus 9 to the 1/2, order of operations says parentheses come first. I have to be able to simplify this before I can take the exponent of 1/2, basically. So that rule basically says that a plus b to the n does not equal a to the n plus b to the n, meaning you can't distribute an exponent that way.
Okay.
All right. So now we got to set this equal to 0 and solve. And this is going to take some pre-calc skills, some algebra. It's not too bad. Here's what I would do. We have two terms there. So anytime you have two terms and they're both rational, I would just move one over to the right, and then you can cross multiply, right? So we have x. Oh, you have to be kidding me. My Apple Pencil ran out of juice. All right. Going with using my hand here, so handwriting is about to be worse than it was. X over 6 root x squared plus 9 equals 1/8. And then we're just cross multiplying, right? So we're getting 8x equals 6 root x squared plus 9. All right, pre-calc stars. You with me, Bonnie? Where do I go from here? X equals 6 root x squared plus 9. Help me out. Somebody help me out. What do I want to do to continue to solve this? Yeah, you can divide the 6, sure. All right, so I have 4/3 x equals root x squared plus 9. What's next? Yeah, we want to get rid of that square root, so I'll square both sides. So I got 16/9 x squared, sorry, equals x squared plus 9. And now I have like terms. I can subtract over the x squared. So what's 16/9 x squared minus 1x squared? So that's just 16 over 9 minus 1. Or 16 over 9 minus 9 over 9. 7/9, right? 7/9 x squared equals 9. Now we want to do what you were talking about earlier, Ian, which is multiply by the reciprocal, 9/7. You don't like it, Vincent? X squared is 81 over 7. Take the square root. We can discard the negative one. We already said we don't want x to be negative. Square root is going to be 9 over root 7, right? Hey, real life contextual math doesn't just come out to whole numbers. All right, we've one critical value. And this is a closed interval. So rather than use the number line and verify that this is a minimum, I'm going to use the closed interval method, which is just, we're going to test this in our time function. We're going to test the endpoints in our time function. And whichever one gives us the least amount of time is going to be our minimum, right? All right. So off to the side, I'm going to write out what I'm going to do. Hello.
2 for each student.
Okay, thank you. That's in this class?
Yes.
Okay. So I'm going to write out, what we want to look at is the endpoints. So t of 0, and I'm going to make a note. The only reason I can use this method is because it's on a closed interval. So this is the closed interval method. So t of 0, I'll test that endpoint. T of 8, I'll test that endpoint, and then I'll test our critical value, t of 9 over rad 7. Each of these will give me a time it takes to get across and to point B. Whichever one's the smallest is going to be my answer. So, all right. It's going to be best to do in the calculator. We're going to go to our calculator. We're going to enter our time function. Which is kind of nasty, but that's okay. Our time function is square root x squared plus 9 and get out of the square root divided by 6 plus 8 minus x over 8. So open parentheses 8 minus x over 8. All right, and as long as you've got that properly entered, we can now go to our table. Just going to delete this stuff. All right, now we can just input our x. X being, remember what x is, it's the landing point or the distance below straight across the river that we should land, right? We input the x and that will output the time it takes in hours, because our units are in kilometers per hour, in hours that it takes to get to point B. All right, so let's do that. So if x is 0, this is the case where I just rode directly across the river and then run straight down. So the least efficient distance-wise, but we'll see what time it gets us. It's going to take us an hour and a half. We'll go 8. This is if we just row straight to point B, no running at all. The most efficient distance-wise, but again, we row much slower than we run. Oh, that's a little faster. 1.424 hours. And then we'll do our critical value, which tells us to land at 9 over root 7 kilometers below our starting point, which I don't know what 9 over root 7 is. We'll see approximately. That's the most efficient. So basically, if we land 3.4 kilometers below point B, that's the way we can get to point, what, D, the fastest. No, below point C, I'm sorry. All right, so where should he land to reach B as soon as possible? So hold on, let me copy down these answers. So 1.5, 1.424, and 1.331. All right, so final answer, here we go. I basically don't have any space to write this, but I'm gonna write it down here. He should land about, what was that x value? What was 9 over root 7? 3.402. So he should land about 3.402 kilometers below point C. What do you think? Did I call it right? Is that the most challenging one so far, or was maybe the cylindrical can just as challenging as that one? All right, these are a lot. Let's take a break. I haven't given you guys a break. Takes the form of a right circular cylinder with both its radius and height changing with time. And then it tells you to note that here's the volume formula for a circular cylinder. A recovery device on the scene, a recovery device arrives on the scene and begins removing oil. The rate at which it is removed is R of T equals 4,000 root T cubic centimeters per minute, where T is the time in minutes since the device began working. Oil continues to leak at the rate of 2,000 cubic centimeters per minute. Find the time T when the oil slick reaches its maximum volume. Justify your answer. Okay. So we want to figure out when the oil slick reaches its maximum volume. So the first thing we need to think about is overall. So you have this big oil slick, and basically you have oil spilling out, and at the same time we have some machine that's removing oil, right? So what I want to think about is the overall change in the volume of that oil slick. So we have like our big oil slick here, and it's like, it's not just, it has thickness, right? Like even though oil will sit on top of the water, it will have some like, it'll be super thin height, but it will have thickness. Therefore, it's a cylinder, not just a flat circle. Does that make sense? And so you have oil spilling out. Here's the Exxon Valdez with a big crack in it, spilling oil into the Baja coast. Those are drops of oil. And then you have some machine, let's say it's a straw. There's my straw. And that's sucking oil out, right? And so oil is coming in and going out at different rates. Now, we're given the rate at which oil is going out. That's R of T. That's already a rate. What's the rate that oil is spilling in? 2,000 cubic centimeters per minute. So the overall rate of change in volume, I'll call that dV/dt. That's my overall volume rate of change of my oil slick is just going to be the rate that it's going in minus the rate that it's coming out, right? So that's just going to be 2,000 minus R of T. All right, notice that this is already a derivative. It's already a rate of change. So I already have the derivative of my overall volume function. If I want to find a maximum, normally what I do is build a function, take the derivative, then what? What's that? Set it to 0, right? Find the critical values. So I'm just going to take that, I'm going to set it to 0. Okay, so then 2,000 equals R of T, yeah? And so this is where using your calculator could be helpful. You could probably solve this by hand. I could plug in 400 root T, solve that by hand, right? You can also just use your calculator and plug in 2,000, plug in 400 root X, and find the point of intersection. Actually, it might be easier to do this one by hand, to be honest with you. Let's see, 2,000 equals 400 root T. Divide out the 400, what do we get? Five equals root T. Square both sides, T equals 25. Just 25, right? All right, so now let's check. At time 25, and we're going to check dV/dt here. At time 25, dV/dt is 0, right? So let's take a time to the left of 25. Maybe time 20. So when I plug in 20 for T into R of T, that'd be 2,000 minus 400. 2,000 minus 400 root 20. That's 211, so that's positive. That means overall my volume is doing what? So the derivative is positive on that interval. So what's going on with the volume? It's increasing. So basically what we can say is from the time the oil began to spill to time 25, my oil slick is increasing in volume, right? All right, then let's check after 25, maybe 30. And again, I'm just plugging in 30 for T and R of T. So I'm plugging in 30 here. I'm going to have 2,000 minus 400 root 30. And in my calculator, that gives me negative 190. So I'm negative, which tells me that my volume after 25 is decreasing, right? So my volume at time 25 is at a maximum. Does that make sense? Now we have to justify our answer. Is the number line enough for the AP graders as a justification? No, you just need to kind of verbally explain how you know. So we're just going to say the volume is at a max at T equals, what are our units here? Do we have units? So its time is going to be in minutes. So time equals 25 minutes. Since when T is less than 25, dV dt is positive, and when T is greater than 25, dV dt is negative. And that's it. So we just kind of have to verbally explain our answer there. All right, so there's an example of an AP style question. I think this is from the 2017 exam. I mean, pretty similar to the examples that we've been doing. Again, they will play little tricks. Like they gave us the volume formula of a cylinder. We didn't need that because the rate of change of volume was a constant. We just needed that 2000. So you just have to continue to practice these problems to kind of get a handle on them. All right, folks, you should be able to finish the problem set now. Go ahead, Ian.
So since when T is greater than 25, the derivative is negative. If it was still positive but still less, how would you write that out in the final statement?
It would be what do you mean?
So if
it was
at 30, if it was still less, so we have the same answer, but it was positive, so you can't say dV is less than 0. You can't say greater because that doesn't prove.
That just means that the volume would be continually increasing. So like that would be the case.
That's at 0 there. Okay.
Right, yeah. It would just mean that, right, we're not taking it out as fast as it's being dropped into the water.
Yeah.
Good question. All right, so you should have be able to finish that problem set for 5.10, 5.11. I have office hours tomorrow from 11 to 12:30, 11:10 to 12:30. So feel free to either pop in on Zoom or you guys come in here and see me if you like to work on those problem sets. Other than that, unless you have questions, feel free to log off, Zoomers. Finish up that problem set. I'll take questions over at the beginning of next class as well.